Today's lesson is on vectors. Vectors are super important when you guys go into physics. So we'll be touching on them a little bit in Precalculus, but you can do much, much more with them. So this is an important concept used every day in the world. It's both, a vector is a quantity that has both a magnitude and a direction. An example would be where we constantly use vectors when we talk about the speed of planes, which is the magnitude, but also the direction that they're flying. So anything that has like a speed and a direction, we'll use a vector. The point 2, 3 represents a position in the coordinate plane. So if I have the point 2, 3, it's right here. But the vector, so as you see, it has like a different notation, not parentheses, but the little arrows, represents a directed line segment. Its tail would be at 0, 0, and the head, or the tip, would be at 2, 3. So this would be the vector 2, 3. And we'll talk about how vectors can move around and so on, but that's the basic vector 2, 3. Okay, so the magnitude is just going to be the length of the vector. So if you think about 2, 3, it goes over 2 and up 3. So if we want to find how long this vector is, all we do is we do 2 squared plus 3 squared, and then we take the square root. So the magnitude can be found by the square root of x squared plus y squared. And then the direction, we can find the angle right in here by doing opposite over adjacent. So we say tangent of theta equals opposite, which is y, the y value, over the adjacent, which is x. But we just need to make sure that we take note of what quadrant we're in. Because if you remember, tangent has a period of 180 degrees or pi, right? So you might get the wrong value at first. So you always want to think about the quadrant that you're in. Okay, so vectors can be written in several different ways. Sometimes you might see a bold letter, like U in bold equals the two components U1 and U2. Sometimes you might see a ray symbol, so with a U with an arrow above it. Other times you might see the letters I and J to represent the x and y components of the vector. So if you see negative 2i plus 3j, it really represents the vector negative 2, 3. So I know it's all very confusing, but different people were studying vectors at the same time, and so there's different notations that books will use. Okay, so number 1, so it says sketch the following vectors and find their directions and magnitudes. So if needed, round the angles to 3 decimal places. Okay, so we'll go ahead and do a little rough sketch. So if I have 5, negative 12, I go over 1, 2, 3, 4, 5, and I go down 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, running out of room, 11, 12. All right, and it's a vector, so it's going to start at 0, 0, and it's going to go towards that point of 5, negative 12. Okay, so it looks like that. So that's the vector. Oops, negative 5, positive 5. Okay, and we need to find both the direction and the magnitude. Okay, so for my angles, I'm going to go ahead and have you do it between 0 and 360. All right, so you don't have to do radians for this section. All right, and we said the length ends up being just the length of this line, which you can find by Pythagorean theorem, right? You have 12, or negative 12, and 5. So we call that the magnitude. Okay, and we notate it by 2 lines, kind of like the absolute value. And some books actually call it the absolute value too. All right, so we get the square root of 5 squared plus negative 12 squared. So we have 25 plus 144 is the square root of 169, which is 13. So that's the magnitude. And then the direction is our theta. So theta is going to be the y value over the x value. So if you do that, if you do inverse tangent on your calculator of negative 12 over 5, you get an angle, let me find it, of negative 67.380. And that's kind of what we want, but I told you that I want your angles between 0 and 360. So we're going to add a rotation of 360 degrees to it. And when we do that, we get 292.620. So always be careful and think, is that the quadrant that I want? So the fourth quadrant is between 270 degrees and 360 degrees. So yes, that works. It is in the fourth quadrant like we want. Okay, so the next one. So I have 1 comma square root of 3. That means I go over 1 and I go up square root of 3. Square root of 3 is around 1.7. So it's that vector right there. So we're in the first quadrant. So if I come up with the magnitude, I have the square root of 1 squared plus the square root of 3 squared, which ends up being 1 plus 3 is 4. So the square root of 4 is 2. So that's our magnitude. And then our direction, we find tangent of theta equals the y value over the x value. So when you find theta, you get 60 degrees. And that makes sense. It's the first quadrant, so that is our theta. So the next one is written in that different form. So I want to try to mix it up a little bit sometimes. So this is the point, or the vector -2, -6. So if we talk about the magnitude of that vector, we're going to have -2 squared plus -6 squared, which ends up being the square root of 40, which we would simplify as 2 root 10. So that's the magnitude, and then the direction, we have tangent of theta equals -6 over -2. So theta equals inverse tangent of 3. And when you find that, you get 71.565. But this is why I tell you that you should always draw the vector, or at least think about what quadrant it is in. So we have -2, -6. Okay, here's my vector. It's in the third quadrant. So when I get something that's 71.565, that's not what I want. That is the angle right here, right? That's not what I want. I want the other way, right? So what I need to do is, instead of rotating all the way around 360 degrees, I actually just need to add 180 degrees. So when I do that, I get 251.565. So that's the theta that we're actually looking for. So be really, really careful. And then some of them look like they're going to be a lot of work. So you think you have to do all the same work that you did on the last problem, but you actually don't have to. So I always like them when they're along the axis, because this one I can tell that the length of it, right, the magnitude, is just 4. I went down 4 units, right? And then I can tell that my direction, my theta, is along the 270 degree line. So this one is actually very easy, and you can do all of the math behind it and you'll get those numbers, 4 and 270. All right, so the next thing we have, so it says vectors don't always have their tails at the point 0, 0. So vectors can be all over the coordinate plane, and we can move them to wherever we really need them. Okay, this will make more sense when we talk about the airplanes and so on. So suppose we have the vector 3, 4. Okay, the most basic version of it does start at 0, 0, and it goes up to the point 3, 4. Okay, but we could have different forms of this vector, so it could really start wherever we want it to start. So maybe I start down at -4, or 0, -4. Then I would go over 1, 2, 3, up 1, 2, 3, 4, and it would be that vector. Notice how they have the same direction, they're pointed in the same direction, and they have the same length. Okay, so they're the same vector, they're equivalent. Okay, so I could have maybe 1, 2, 3, 4, 5, 2, and I could go over 1, 2, 3, up 1, 2, 3, 4. So I could have this vector. It's exactly the same. Okay, so there can be lots of different forms of the same vector. So maybe I start at 5, I go over 1, 2, 3, up 1, 2, 3, 4. That would be another one. Okay, all of these have the same direction and the same magnitude. All right, so it says find the vector AB with the points -2, 0, and -6, -7. So we're going to use a sketch and we're going to try to find the most simplified form of the vector AB. Okay, so if I start at -2, 0, that's my A, and then I go to B is -6, -7. Okay, this is what my vector looks like. Okay, so I start at A and I go through B, or to B. All right, and I want to find that vector starting at 0, 0. Okay, so basically I want to know how much it moves down and how much it moves over. So it moved down, it went from 0 to -7, so it went down 7. And it moved left, it went from -2 to -6, so it went left 4. Okay, so the vector would be the same as if I started at 0, 0 and I moved it down 7 and left 4. Oops, I need a little bit. My drawing's not very good. Okay, and that would be exactly the same vector. So that means that AB is really -4, -7. Okay, so let's think about what we did to find AB. And let's do it for the next one. So I've made this B, it should be, or D, it should be CB. So the next one, I want CB. Okay, so if I do the sketch, I have -3, 4, and I have 5, -10. So we're starting at C and going to B. So if I talk about vector CB, I want to know how far it goes down and how far it goes over. Okay, it goes over, let's see, from -3 to +5, so it goes over 8, and it goes down from 4 to -10, so down 14. So the vector ends up being 8, -14. It's like you move it, starting at 0, 0, it would go over 8, down 14. Okay, so what we're doing here is we're taking the second point and we're subtracting out the first point. That's opposite of slope, so don't think y's minus y's first and then x's, right? It's still x's and then y's. Okay, so I have my head minus my tail. Okay, so I'm going to have 8 and then minus -14. All right, so if I do EF here without drawing the sketch, I would have 0 minus 0. And then I'd have 0 minus, actually not 0. Sorry, start with the tip, -7 minus 0. So I get 0, -7. Okay, so EF is the same as just F, like the vector going from the origin to F because E was the origin. Okay, so those are my vectors. All right, so the next part, so it says the head minus tail rule. So it says if an arrow has initial point, x1, y1, and terminal point, right, the terminal point on the ray, x2, y2, it represents the vector x2 minus x1, comma, y2 minus y1. Okay, so on the next little bit, it's a little bit hard to see these. Let's make this one y, w, v, and u. Okay, so a little bit hard to see them, and I think I made a typo. So y. Okay, and it says find the component form of each vector and then find their directions and magnitudes. So I'm not going to do the directions and magnitudes for all of them, but I'll do it for one of them. So I'll do w first. Okay, so if I'm finding vector w, okay, what I need to do is my head minus my tail. So I need to find all of these points. Okay, and that's kind of the step I did first because it's a little bit hard. I had a grid on mine, but the grid didn't really transfer very well in your notes. So let me go ahead and tell you what these are. So you can kind of see the grid. So this first one is going to be -7, -1. This point up here is -9, 8, 4 comma 8, 1 comma 0, obviously 0, 0, 1 comma negative 8, and then this one right here is going to be negative 5, negative 2. Okay, so we're going to need those different points. All right, so for W, if we do the head minus tail, it's going to be the negative 7 minus a negative 8, and then it's going to be negative 1 minus 8. So we end up getting 2 comma negative 9. And you can think about what it looks like if you had 2 comma negative 9. It would look like a vector like that, right? Which does look like this vector. It's just been moved. It's in a different location. Okay, so no big deal. All right, so if I wanted to find the direction and the magnitude, if I first find the magnitude, it's going to be the square root of 2 squared plus negative 9 squared, which is going to be 4 plus 81. So it's going to be the square root of 85. Okay, and then the direction is going to be the y over the x. So if you find theta, you end up getting negative 77.471. But we always said between 0 and 360, not that it totally matters, but we'll add 360 degrees to it, because remember, if I talk about 2 comma negative 9, it's in the 4th quadrant. And so I get 282.529. Okay, so obviously this is a lot of work to find it for each of these, so we'll just find that for W. The rest of them we'll just find the component forms. So component forms means the x and the y coordinates when it's set up as a vector. Okay, so if I find V, okay, V is going to be, this one does start at 0, 0, so it's just negative 9 comma 8. And then U is going to be 4 minus 1, 8 minus 0. So it's 3 comma 8. And then Y, so the tail, or the head minus the tail, so I have 1 minus a negative 5. And then I have negative 8 minus a negative 2. So I get 4 comma negative 6. Wait, did I mess up on my 1 minus a negative 5? Oh, what am I doing? 1 minus a negative 5 is 6, right? I don't know what I'm doing. So we get 6 comma negative 6. All right, so those are the different component forms, and you could find the direction and the magnitude for each of those as well, but we'll go ahead and skip that. All right, so it says sometimes vectors don't have to have the same components, but they have equivalent lengths in vectors. So we talked about this briefly. This means that vectors are said to be equivalent. So basically, you can just find their component form, and you see if the component forms are the same. So number 1, it says for the points negative 2 comma 0, 4, 0, negative 3, 1, and negative 1, 3 are the vectors A, B, and C, D equivalent. So for A, B, I'm going to do my head minus my tail, so 0 minus a negative 2, 4 minus 0, so I get 2 comma 4. And then for CD, I'll do the same thing. So I'm going to do the D minus the C, so I'm going to have negative 1 minus a negative 3. Then I have 3 minus a negative 1. So when I do that, I get 2 comma 4. So yes, they are equivalent, because if I drew them, if I moved them, they would go to the same location. They would both be right here. So if I move them so the tail was at 0, 0, you would have exactly the same vector. Okay. So adding and subtracting 2 vectors is exactly what you would think it would be. So if you have 2 vectors, u and v, and you're asked to add them, the sum, u plus v, ends up being the 2 x components added together and then the 2 y components added together. So in this case, u1 plus v1, and then u2 plus v2. Okay, and the same idea for subtraction, you would just subtract. The product is going to be where you have some kind of number out front, so u1, u2, and you can actually bring the k into both of them. Okay, kind of like the distributive property. So you're going to have KU1, KU2. Basically, all a scalar does is it makes the vector longer. So if I had U was only this vector from here to here, if I talk about 3U, I'm going to have 1, 2, 3 of them in that same line. Okay. So it says there are two different geometric representations of vector addition. So one is called the tail-to-tip representation, and this is usually what I use, the tail-to-tip. So in this representation, we move the second vector to the end of the first vector, and then draw a line from the tail of the first to the second. So maybe you have two vectors, and you have one here and then one here. And I want to find A plus B. So what I do is I take this vector B, and I move it to the end of A, and then I find what I call the resultant. So that vector that I just drew in that connects from the tail to the tip ends up being A plus B. So that's what this drawing right here is. So it's the tail to tip method. Okay, but another method is the parallelogram representation, and some books really like the parallelogram representation. So it's really up to you on what you use. So in this representation, each vector can start in their standard form with their initial points at 0, 0. Then you form two other sides to create a parallelogram. The resultant, or the sum, is then the diagonal directly between the two original vectors. So if you see, it's kind of like the tail to tip thing. It's like moving, maybe you move A to the end of B, or you move B to the end of A. It doesn't matter. Either way, this diagonal is then the resultant. So you don't have to worry about the tail to tip when you draw that parallelogram in. It kind of takes care of it. Okay. So it says, suppose U is 5, -2, and B is -3, 4. So I'm going to sketch this out so you understand what we're doing when we're adding these vectors. So I have 5, -2, and I have -3, 4. Okay, so this one was U, and this one was V. Okay, if I want to add U plus B, what I can do is I can create the parallelogram, or I can do the tail to tip. So I'm going to do the tail to tip. So I'm going to take V, and I'm going to move it to the end of U. So that means that I'm going to go over 3, 1, 2, 3, and up 4. I went up too far. Okay, so I moved it to the end. And the resultant is connecting from the tail to the tip of the very end. So you go tail to tip, and then this goes from the tail of the original to the tip of the end. Okay, and as you notice, it looks like 2, 2. So let's see why. So if I have 5, -2, and I add it to -3, 4, you do exactly what you would think you would do. You add the two x's, and you add the two y components. So you get 2, 2. So it works out. All right, now if you have 4u, so like I said, u was 5, 1, 2, 3, 4, 5, -2. What that does is it creates 4 of those u's lined up. Because if I had u plus u, it would just be tail to tip like that, tail to tip, tail to tip. So there would be 4 of them. So what does that become? Well, it means that we went out 4 of those 5s. We went out 20, and we went down -8. So if I have 4u, all I'm doing is I'm bringing that 4 in, and I'm getting 20, -8. Okay. So it makes sense on how we would add these and multiply and so on. All right, so I won't draw the next two, but we will use the formulas. So if I have, let me write what u was. So u was 5, -2, and v was -3, 4. So if I have 2u minus 3v, then I'm going to have 2 times u is 10, -4. And I'm going to do plus, and I'm going to multiply the -3 in. So I'm going to have 9, -12. So I get 19, -16. And then negative v ends up being the opposite of v, which ends up being 3, -4. Okay? So far these vectors that I have a certain magnitude, a certain length. So if I wanted to find the length of part B, 3, -4, its length would be 5. I would do 3 squared plus -4 squared. Under a square root, I would get a length of 5. But sometimes we want a unit vector. We want things to be a length of 1, okay? And in order to do that, we just divide out by whatever length it was. So if it was 5, we would divide by 5. So this last one, it's unit vector. If I divide by that length of 5, I'd have 3/5 and -4/5. I just divide it out. So then that way it's a length of 1. Okay, so for this one, it says a vector with a magnitude of 1 is called a unit vector. If v is not a 0 vector, then the vector u ends up being whatever v was divided by the magnitude of v. Okay, so it says find a unit vector in the direction of 5, -2 and verify that it has a length of 1. So if we have 5, -2, okay, it doesn't have a length of 1. Okay, it has a length of the square root of 29. Okay, you can find it, 5 squared plus -2 squared is 29, square root. Okay, so square root of 29 isn't 1. So what if we want it to be a length of 1? Then it would be a little tiny vector going in that same direction. Okay, but it will only have a length of 1. So what we do is we find u usually stands for unit vector. And I'll put my little arrow over it because I can't really bold it very well. All right, so I'm going to do v, which was 5, -2, and I'm going to divide by the square root of 5 squared plus -2 squared, which I said was the square root of 29. So your answer ends up being 5 over the square root of 29, comma, -2 over the square root of 29. Okay, I would leave it like that. Some people like to rationalize, and I don't know what Math Excel is going to make you do, but you might have to do 5 root 29 over 29, -2 root 29 over 29, if they don't want square roots on the bottom. All right, so it says verify that it has a length of 1. So we're going to check. You don't usually have to do this. So if I want to see that it has a length of 1, I want to do the square root of a squared plus b squared. So I'm going to have 5 over the square root of 29 squared plus -2 over the square root of 29 squared, which is 25 over 29 plus 4 over 29, which does give you the square root of 29 over 29, which is the square root of 1, which is 1. Okay, so it does work. It gives you a unit vector when you divide by the length. Okay, so let's say we have something that's backwards. So it says previously we found that the angle of a particular vector using the formula tangent of theta equals y over x. But what if instead we had the angle and the length? How could you find the component form? And it's actually pretty simple. Okay, it kind of goes back to what you learned a long time ago, SOHCAHTOA. So suppose we know that the angle is 25 degrees and the length of the vector is 10. Okay, we want to find the component forms. So I'm going to call them just x and y for convenience. So how do I find x and y? Well, I use SOHCAHTOA, right? So I'm going to find, if I want to find x, then I do cosine of 25 degrees equals adjacent over hypotenuse. So x ends up being 10 times cosine of 25 degrees. Okay, you don't have to find it, but go ahead and think about what we did there. We did the length, the magnitude, times cosine of 25. And if I want y, it's sine of 25 degrees equals y over 10. So it's going to be 10 times sine of 25 degrees equals y. So that's how we get the component form for a vector. If you have the angle theta and the length, then you can do the length times cosine theta, the length times sine of theta to get the x and y components. So number 1 says find the components of the vectors with the given characteristics. So if I want to find the component form, what I'm going to do is I'm going to say the length was 3, and I'm going to say cosine of pi over 6, and then 3 times sine of pi over 6. Remember, cosine is x, sine is y, so you can keep it straight like that. So cosine of pi over 6 is root 3 over 2. Sine of pi over 6 is 1/2. So we get 3 root 3 over 2, comma 3 over 2. Okay, so the next one, its components can be found by 100 cosine of 300, 100 sine of 300. If you talk about 300 degrees, oops, wrong place. 300 degrees is here, 60 degrees away, right? So we're going to say it's 100 times 1/2, and then 100 times negative root 3 over 2. So we get 50 comma negative 50 root 3. Okay, and those are my two answers. Okay, so pretty easy finding the component forms. Okay, so number 2 says a hot air balloon is rising vertically at 13 feet per second, while the wind is blowing horizontally at 4 feet per second. Find the speed v of the balloon and the angle theta it makes with the horizontal. Okay, this is very simple. The speed is just the hypotenuse here, and the angle is our theta that we have drawn in. So if I want to find the speed, what I'm finding is the magnitude, right? I'm doing 4 squared plus 13 squared under square root. So when I do that, I get 16 plus 169. So I get the square root of 185. So if I want a decimal approximation, I'm going to have 13.601 feet per second. Okay, it seems a little bit more like, you know, if you're telling someone how fast you're going, you don't usually say the square root of 185 feet per second, like you usually do a decimal. Okay, and then the angle theta, we do tangent of theta equals the y value over the x value. So when you find this, you get 72.897. Okay. All right, number 3, it says a vector w of magnitude 150 points southwest. Okay. Southwest, we assume to be directly south and west. Okay, so directly in the center. So when you see something like southwest, northeast, blah, 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 you want to find the angle. So our theta is going to be 225 degrees, right? 180 plus 45. So it says resolve the vector, you might hear it written that way, resolve the vector into southerly and westerly components, round to 3 decimal places. So what it's saying is find the component form, find the x and the y. Okay, so I'm going to do the component form is going to be 150 cosine of 225, 150 sine of 225. So I have 150 times negative root 2 over 2, and 150 times negative root 2 over 2. Same number, right? Third quadrant. So we can simplify and we can say, oh, well, that's negative 75 root 2 and negative 75 root 2. But I did say round to 3 decimal places. So if you find that, it's negative 106.066. And we write it twice, right? So that is my southerly and westerly components, my x and my y's. Okay, so vectors are used whenever we're dealing with objects traveling at a certain speed, like I told you, like airplanes and boats. The magnitude of the vector is the speed. So clearly we want to know what direction planes are traveling to avoid collisions and estimate how long it will take for them to arrive at their destination. So now you see why air traffic controllers are so stressed with their jobs, right? There's a lot of math with this. In order to do this, we use bearing, which we've talked about before. So remember, bearing, we could say 2 different ways. So one way is to say, maybe you do, I don't know, what am I trying to do? 155. Okay, this would be a bearing of 155 degrees. Okay, you go from the north line and you go clockwise. Okay, but you might also see it written as south 25 degrees east. And when you see that, what that means is you go along the south line and then you go 25 degrees east of that. Okay, I think I try to stick with this first notation in this section, so no worries. All right, so it says starting at port A, a ship sails 44 miles on a bearing of 190 degrees. Okay, so it's a little tricky to draw. I'm going to draw it kind of tiny. Should have given myself much more room. So we're going here. So we've gone 10 degrees west of south, right? And then all of a sudden it turns and it sails 34, sorry, I should have miles, on a bearing of 344 degrees. All right, so now we have a new little bearing. So now we're going to go 334 degrees. So you're going to go around to here. Okay, so we made this sharp turn. Now 334 degrees, if you want the angle maybe right here, that angle is going to be, let's see, I gotta think about it, 64 degrees, right? Because I did 334 minus 270. Okay, and then it goes for 34 miles. So find the distance of the ship from port A. So I'm going to make this line look a little bit shorter than what it does, because the first one was 44, so that was a little bit longer than this next one. Okay, so that's the distance I want to find. Okay, so I'm going to kind of zoom in and show you what I have so far. So I want to know this x value. I have a line going like that, and then I have a line going like that, right? And I know that this one's 44, and this one's 34. And the angle right here is 64 degrees. And here's where it gets a little bit complicated, because we know that this angle in here was 10 degrees. So you need to find this angle right here, which is 80 degrees. That allows you to find the key angle in the middle. So you want to do 64 plus 80, and then subtract from 180, and you get 36 degrees in there. Okay, so we have 36 degrees, we have 44 as this length, we have 34 as this length, and we want to know x. So the easiest way to do this is something that we've learned before. It's the law of cosines. So this one was just complicated. It doesn't actually use the vectors, because I didn't say miles per hour, I said miles. It's a little tricky. I'll talk about when we have miles per hour, what we can do with vectors. Okay, so we're going to sketch it out, and we're going to say, okay, well, I have x squared is 34 squared plus 44 squared minus 2 times 34 times 44 times cosine of 36 degrees. So when you do that, you get x is equal to 147 5.616. So when you take the square root, you get x is equal to 38.414. All right, and that's in miles. That'd be really hard if I had kept it originally miles and kilometers, because I made this little error here, because you'd have to convert, but we'll change that original to miles. Okay, number 2. An airplane has an airspeed of 130 kilometers per hour. So let's talk about the airplane first. And it's going on a bearing of 64 degrees. So that means this angle is 64 degrees, and we're going 134 kilometers each hour. Okay, however, there's a wind that's blowing it a little bit off track. So when we talk about the wind has a bearing of 334 degrees. I like this 334 apparently. So that's the one with 64 here, right? 334. Oh, I did it too far. 334 is here, right? So you find it by doing 334 minus 270 to get to 64. All right, and it's going to go 26 kilometers per hour. So what happens is we're pushing this original line, we're pushing it a little bit off course in this direction. and we're getting a resultant vector where we add those two vectors together. Okay, but we don't want that. It says, what must the airplane's actual bearing be in order to maintain this current track? So you kind of have to think in reverse. You have to say, okay, I want to go against the wind and I want to undo the wind. So if I'm undoing the wind, what I'm doing is I'm taking the airplane, which I'll call A, vector A, and the wind, which I'll call vector W, and I want to subtract out that wind. In other words, I want my airplane originally to go there. I want it to go a little bit off course in the opposite direction. So when I do that, when the wind pushes it back, it will be on its current track. Okay, so I want to do A minus W. So let's find what A is and what W is. So vector A, its component form, I cannot use, well, I can use 64. Actually, I can't. Okay, that's not up on my notes. Okay, what I need to do is I need to think about its angle with our normal, like from the x-axis. That's what can be a little bit frustrating about bearing, because it's not 64. Here's where 64 is, right? It's actually this angle right here. So we're going to use the angle of 26 degrees, right? So I'm going to have 130 is my magnitude, and then I'm going to have cosine of 26, comma, 130 sine of 26. And then the same thing for the wind. So the wind, we knew that this was 64. So what angle is this? 180 minus 64. So it's 116. So its wind is going to be component form 26 cosine of 116, 26 sine of 116. So when I subtract them, vector A minus vector W, I can just kind of write it all together. I don't have to do this separate and find the decimal versions. I can put it all into my calculator all at once. So make sure that you are changing from the bearing to our normal angle measurement. Okay, so when we find this first one, we end up getting 128.241, and then the other one is 33.620. Okay, so that is the bearing that it should go in order to maintain the current track. So then if I ask for something like the direction and the speed, then I would find the magnitude and the theta, right? So you could ask this lots of different ways, but oh, I guess that's what it's saying. What must the airplane's actual bearing be? So let's go ahead and find theta, and we'll go ahead and find the speed of the plane too. So your speed is going to be taking each of those values and squaring them, and then taking the square root. So when I found the magnitude, I get 132.574. Okay, so it's going a little bit faster. Oh, actually 575. This is in kilometers per hour. And then your angle, if you find tangent of theta equals the y over the x, I should have found this before. I made a little error on mine though. Okay, so we get theta is equal to 14.690 degrees. But remember, that's not the bearing. That is this angle here. So if you want to find the bearing, we need to do bearing. Bearing meaning, All right, bearing is going to be the rest of the 90 degrees. So in this case, it'd be 75.310 degrees. Okay. All right, so it's pretty close to the 64. It's just like you have to account for the wind, so you have to go a little bit off course. You need to go a little bit further to like closer to that west or the east line in order to correct that. All right, so number 3, it says an airplane is flying on a bearing of 340 degrees at 325 miles per hour. So 340 degrees is going to put it around past 270, almost. So it's 20 degrees away from the north line again. So he's going that way at 325 miles per hour. A strong wind is blowing with a bearing of 320. So there's 40 degrees at 60 miles per hour. Find the component form of the velocity of the plane. So what's happening is you have this really long line going like this, and then you have a shorter line that's coming up off of it. Oops. And it's making it just a little bit off course. So your resultant ends up being like that. Okay. So we need to find what's happening. So we're going to find the airplane's component form, and we're going to add the wind's component, and that's going to give the resultant. So it's going to give this new velocity of the plane. Okay, so that's actually what I'm going to do in part B, I'm realizing. Part A, I wanted find the component form of the velocity of the plane in still air. So if there had been no wind, what would that be? Okay, so the airplane, so I'll call it A, like I did before, ends up being not 340 that we're going to use. We need to use this angle going right here, which ends up being 110 degrees. So I'm going to have 325 cosine of 110, 325 sine of 110. Okay, and you can find those numbers, 325 cosine of 110, 325 sine of 110, and you get negative 149.724 and 351.363. Okay, but B says find the actual ground speed of the plane in the direction of the airplane. So in other words, the plane speed is increased or decreased because of the wind. So we call this the ground speed. Find the direction and how fast the plane is traveling with the wind. Okay, so the wind is pushing it, and it's making it go either faster or slower. So in this case, I think it's making it go a little bit faster. So we want to find how fast the plane is traveling with the wind. So we're going to do the A plus W. So A, we said, was 325 cosine of 110, 325 sine of 110, and we're going to add it to the wind. So the wind, like I said, is going 40 degrees here, which makes it a total of 90 plus 40, which is 130. Okay, so I'm going to have 60 cosine of 130, 60 sine of 130. So you can find all of that, and you should get that it is, oops, I looked at the wrong one for the last one. It's this number that I had up here, negative 149.724 and 351.363. Sorry, you're probably a little confused there. I copied the wrong number. This is what gets me into trouble when I do it ahead of time. All right, so this one is negative 111.157, 305.400. All right, so that is the component form, which allows us to find the direction and the magnitude. Okay, so our magnitude is going to be our speed of the plane. So when you find that, you get 381.933. miles per hour. So I just took the square root of a squared plus b squared, if these were a and b. And then for the theta, I do tangent of theta equals 351.363 over negative 149.724. And you get theta is equal to negative 66.920, which if you think about where our component is located, it's negative and then it's positive. It should be in the second quadrant. And negative 66 isn't in the second quadrant, it's over here, right? So what we need to do is add 180 degrees to it, which puts it at 113.080. But then we're still not totally right because we probably want the bearing, right? So if we talk about these airplanes, we usually say bearing. So our theta is 113.080. But what that means is it's going here, right, 113. So we're going to subtract 90. And when we do that, we get 23.080, which is just that little bit there. And then we're going to subtract that from 360. So 360 minus 23.080 gives you a bearing of 336.920. Okay, so that's how you do those problems. So they can be really, really tricky. I won't have a ton of those on the Math Excel, but yes, that's probably the hardest part of the this section in particular. So we'll do a little bit more with vectors in the next section. But we're not going to get too in depth. I'll let, if you take physics, you'll do a lot more of that. So I'll let Mr. Crawley teach you more about vectors. But it is pretty interesting, and it will be useful when you go on to physics to kind of have this background.